Welcome to The Explainer. We're embarking on a seriously fascinating journey today. We are going to explore a technology that is quietly, but fundamentally, reshaping how our physical world interacts with the digital one. We're going all the way from the microscopic intricacies of bare metal circuits right up to massive, global Internet of Things networks. It's a journey from the micro to the macro, and it's going to be incredibly eye-opening.
So, let's kick things off with a grand question, and I really want you to think about this for a second. How do you actually connect the unconnected? I mean, think about the absolute logistical nightmare of making millions of remote, smart devices talk to each other. If you drop a sensor in a massive agricultural field or deep inside the concrete basement of a smart building, how do you get it to send data back to the cloud without constantly killing its battery or just entirely losing its signal? Standard Wi-Fi just doesn't have the range, and cellular data, it eats way too much power. This is the exact problem we're solving today.
Here's our roadmap for the day. We're going to hit the LoRa connectivity revolution, peek inside the actual hardware module, look at powering the smart home, and finish up with accessible gateways for developers. Let's dive in.
Part 1. The LoRa Connectivity Revolution.
So, LoRa, which literally stands for long range, has pretty much become the go-to wireless platform for the Internet of Things. It explicitly solves the exact limitations you run into with Wi-Fi and Bluetooth. Because it's a long-range, incredibly low-power platform designed to shoot data over miles with a battery life of up to 20 years, it's creating massive business efficiencies across some wildly diverse sectors. We're talking smart agriculture, where sensors are tracking soil moisture across huge farms, smart cities handling streetlights, utilities catching water leaks deep underground, and supply chain logistics tracking assets across entire regions. It's basically the invisible web connecting the physical world right to the cloud.
Moving right along to Section 2, Inside the Hardware Module.
Okay, let's zoom way in. Check out this bare printed circuit board. This is the ILLC68S1-F100H0-S module, and it is tiny. We're talking 21 by 14 millimeters. That is practically the size of your thumbnail. Yet, packed onto that microscopic real estate is a Sonics microcontroller and a powerful Semtech transceiver, working together in perfect harmony. It really is an absolute masterclass in miniaturization.
Now, what's really wild here is the sheer density of the engineering required at the component level. Just look at this complex 42-pin layout. You've got your general-purpose I/O pins, power pins that need strict 2.5 to 3.5 voltage handling, programming pins, antenna outputs, the whole shebang. For hardware makers and engineers, getting this integrated requires some intense precision, custom PCB design, and some really deep technical know-how.
To see how it actually ticks, let's look at the system block diagram, which is essentially the internal engine of our tiny module. The Sonics microcontroller acts as the brain, and it talks directly to the Semtech chip, which is basically the radio voice, using a simple UART interface. They're seamlessly passing data back and forth to take digital info and blast it out into the real world via radio frequencies.
Which brings us to Section 3, Powering the Smart Home.
Let's pull back just a bit and see what this specific piece of silicon means for smart home applications. The absolutely crucial point is this incredibly low number, 4.6 milliamps. That is the chip's active receive current, and it's remarkably tiny. This extreme level of efficiency literally allows remote sensors, like a smart home window sensor or a basement water leak detector, to run for years, sometimes up to a decade, on a single tiny battery. You literally install it and just forget about it.
But contrast that ultra-low power draw with this aggressive number, plus 22 dBm. When this device needs to talk, it uses a highly efficient integrated power amplifier to transmit up to 22 decibel milliwatts. That is a loud, powerful signal that effortlessly punches through concrete walls and multiple floors, giving you super reliable medium-range indoor to outdoor wireless coverage. So it whispers when it's listening, but it definitely shouts when it needs to be heard. These specs really highlight the extreme resilience of the signal. With a massive link budget of 151 dB, which is the total allowable signal loss before it drops, and high sensitivity down to negative 129 dBm, this chip has incredible hearing. Basically, your data gets through even in the most challenging, noisy environments. Plus, its continuous frequency coverage from 150 to 960 MHz means it easily supports sub-gigahertz bands all over the globe.
All right, our final stop, Section 4, Accessible Gateways for Developers.
So we've geeked out over the incredible capabilities of the bare silicon, but how do everyday developers, makers, or even tech-curious business leaders actually use this stuff without an electrical engineering degree? Take a look at this comparison. On the left, you have the steep learning curve of the component level, 42 bare metal pins, custom PCBs, strict voltages. But on the right, we've got the developer level. This is the iFrogLab LoRa USB dongle. It totally bypasses the complex engineering and wraps all that amazing Semtech and Sonics tech into a simple plug-and-play USB package.
I really want to emphasize how this dongle acts as a bridge. Just look at these capabilities. It uses a direct USB interface, meaning you don't need to understand complex LoRa transmission concepts to use it at all. Better yet, no driver nightmares for Mac, Linux, or Raspberry Pi. It has a built-in MCU to do the heavy lifting, and it maintains a staggering standby current of less than 1 microamp. You can literally build an instant LoRa gateway just by plugging this into a standard computer.
And then we have this jaw-dropping performance metric, 15 kilometers. Because it leverages that high sensitivity and power output of the internal chips, this simple little USB stick can shoot data across a 15-kilometer radius. If you're on the ground floor, you can easily blast a signal to the 6th floor or across an entire neighborhood. It's actively replacing messy legacy networks like Zigbee and Z-Wave because it simply punches through walls and distances they absolutely can't match.
Which brings us to the end of our explainer, and I want to leave you with a bit of a provocative thought. We went from a microscopic 21mm chip pulling just 4.6 milliamps to a USB dongle casting a net over 15 kilometers. The barriers to entry have been completely removed. So my question to you is, with a 15-kilometer range sitting right there in your pocket, what real-world project are you going to connect? Thank you so much for hanging out with me on this deep dive. I hope you found this breakdown of LoRa technology as fascinating as I did. Keep learning, keep building, and I'll catch you in the next explainer.